Yeah, in the last lesson we left off at the circumferential or hoop stress, equation 20.1. Now let's talk about longitudinal stresses in the cylindrical pressure vessel. Okay, so what happens here is we have the nature of pressure means that it acts perpendicular to all of these surfaces inside the pressure vessel. So we have internal pressure. This is longitudinal, pushing out on the end, and then radial pressure. That gives us our circumferential hoop stress, if you will, down here. So, okay, so if we were to look at that, the closed end of the pressure vessel contains pressure and equilibrium. Okay, so if we were to derive the longitudinal stress, we would say that the force on the end due to pressure is P equals pressure times the area. The area of the end of that cylinder is really just pi over 4 times the inside diameter squared. This is the pressure over which the area acts. Okay, so if we substitute pi over 4 di squared into this equation right here, we get P equals, that's our force, P equals pressure times pi over 4 di squared, and then that also equals this TL. And when I'm saying TL, that's from this diagram here. We got P, pressure's pushing this way, and then that is reacted here by TL. And what essentially TL is the internal stress of the pressure vessel. So that's what we're showing here, sigma TL and sigma TL. So essentially, the internal pressure P is reacted by stress, longitudinal stress, in the pressure vessel walls. Okay, so TL. So this force is reacted by internal stress. Therefore, sigma L, this is the designation I'm going to use for longitudinal stress, equals TL divided by pi DIT. Okay, essentially, so what this is, pi times di is kind of like the circumference of the pressure vessel, and then times thickness T, that is essentially the area of the pressure vessel that's going to react the internal pressure force longitudinally. So when we solve this for when we reduce this equation here, we end up with equation 20.3. That says our longitudinal stress equals P times DI divided by 4T. Notice that the longitudinal stress is 1/2 of the circumferential stress. If the pressure vessel is spherical, then equation 20.3 is going to be the one you use to calculate the stress. Spherical pressure vessels are a much more efficient shape, in which case the stress is roughly half of a typical hoop stress in a cylindrical pressure vessel. Okay, so therefore, when we're talking about pressure vessel, we have a biaxial state of stress. If we were to look at an infinitesimal element of the pressure vessel, we have this C, which is our circumferential stress, which is our hoop stress, and then we have sigma T, which is our longitudinal stress. So we have a biaxial. Next one. Okay, if the pressure vessel also has an axial load applied to the in addition to the pressure load, then we have an additional tensile stress to the longitudinal stress. So we really get two equations, and you can look at equation 20.4. We're going to talk about an example that explores that possibility. Section 20.3. Let's talk about joints here for a second. Pressure vessels can be made from formed curved plates, usually joined by welding. Welded joints are usually groove joints. They're usually groove welded butt joints. Okay, the joints can be oriented in the pressure vessel either longitudinally or circumferentially. If you see, the stress is much greater on a cylindrical pressure vessel circumferentially, in which case the longitudinal joint will fail before a circumferential joint. Let's talk about a term called joint efficiency. Okay, welds are full penetration groove welds. The reason why they use groove welds is by the time you're done with a groove weld and full penetration, you're going to achieve full strength. Now, full strength, we're going to designate that as 100%. The meaning of full strength is that 100% is the strength of the boilerplate material, in which case the presence of the joint does not weaken the pressure vessel at all at 100%. So JE, or joint efficiency, is the rating of the joint. Now, it's assumed that for most joints, a joint efficiency of 70 is recommended. That's if you don't do any x-rays or anything else. I mean, I'm sure that you can design a joint through quality to be able to look at all of your joints through x-rays, in which case you can get a higher joint efficiency out of it. But if you're not going to x-ray all of your joints, it's good to assume that the joint efficiency is 70%. Now, how do we use joint efficiency? We are going to apply joint efficiency into equation 20.1 for the hoop stress. And then we're going to do an example about that one. See example 20.8. And then finally our last slide, section through a standpipe. Okay, so a standpipe in this case is a tank that's open to atmosphere at one end, and it's full of water or some kind of internal fluid. I'm going to introduce the term pressure head. Pressure head has units of feet, and essentially it's fluid energy that's due to the depth of fluid in the tank. So as you go down in the depth of the fluid, as shown here on this internal pressure, our internal pressure increases with depth. It's just a hydrostatic problem. Okay, so what this equation does here, it allows you to convert head, which is in units of feet, H is in units of feet, into P, which is units of pressure. So you can go into equation 20.1 for a standpipe. See, equation 20.1 has the pressure in here, and then this hydrostatic pressure is what we're going to be using. Even though the vessel itself is not pressurized, the vessel does have pressure by virtue of the depth of the fluid in the vessel. And we can do that by converting head into pressure in PSI, by taking head in feet and multiplying by 4.433, and that will give us pressure in terms of PSI. And we'll have an example on that one too. Okay, so this concludes the last lesson in advanced strength of statics and materials. It's been a real pleasure. I think I've gotten a little bit more comfortable with these videos as we went along, but I want you guys to have a great break between semesters, and again, it's always been my pleasure to have you guys in my class. Thank you. I appreciate it.